Hi all, this is Will from LangChain. Let's build computing Olympiad agents together. So about a week ago, this team out of Princeton came out with a paper called Can Language Models Solve Olympiad Programming? It was done by the folks such as Quan Shi and Shunyu Yao, who you might recognize from the React paper, Tree of Thought paper, and Reflexion papers. This paper really has two interesting components to it. On one hand, it's a dataset paper. They come out with this challenge benchmark of 307 competitive programming problems from the USA Computing Olympiad. And they showed that GPT-4 only has about an 8.7% pass rate when trying to do this with a simple zero-shot React agent framework. This is in contrast to some of the existing benchmarks like Human Eval, MMLU, that are mostly saturated by this crop of language models. They then show some inference optimizations, basically prompting techniques or systems engineering types of approaches to improve the performance on average from that 8.7% up to 20.2%. And we'll go more in detail on each of those techniques as we go throughout this tutorial. Let's get a sense for the difficulty of the types of problems in this benchmark. All right, so here's an example question. You can see they're mostly word problems that require you to identify the underlying mathematical problem you need to solve, use advanced data structures and algorithms, and compose them in a creative way to come up with the correct solution. It also has to be done and implemented in a way that solves it within a given time limit. As you can see from this diagram, there's a lot of different usage of sets and other types of things there. The questions are challenging. There's a reason why it's called an Olympiad. What I find interesting about this benchmark is that it really pushes LLMs to the limit. So you can see where it breaks down. I think when we're using them in normal life, you often start to anthropomorphize them and see them think that they're reasoning. Whenever you get to this extent, you can see when they start doing things that look like interesting, close to correct, but don't have this logical property. So as I mentioned before, when they first run GPT-4 on each of these problems, it gets a really low pass rate. They later show a number of inference techniques that they could do to improve it. Some of these include self-reflection, and some of these involve retrieval, either from semantic knowledge or episodic knowledge. They do a lot of experiments to show what types of retrieval actually improve the performance of the model. We're going to implement the best performing retrieval type, this episodic knowledge type, since it seems to be very complementary to self-reflection and works well within our tutorial structure. Let's check out our LangGraph docs to see how we're going to implement this in the tutorial. All right. So for the remainder of the video, we're going to be creating an agent to solve these types of competitive programming problems. We'll break it down into three parts, following the paper's structure and making agents that are increasingly capable of solving these advanced questions. In the first step, we'll implement the reflection agent. It's a zero-shot agent that does self-reflection. This corresponds to here, this block in our graph that we're going to be creating. It's going to have two simple nodes and just run in a loop until it can solve the answer correctly or ran out of time. This is roughly analogous to this reflexion agent they created that gets about a 12.38%. So again, better than the base zero-shot agent, not as good as what they can get overall. In part 2 of this tutorial, we're going to implement retrieval as a form of episodic memory. That's what the paper calls it. This is part 2 here, where we'll be then retrieving some high-quality examples to include within the prompt and hopefully induce better logical performance in the model. This is analogous to this section here that gets about the 22.2% on the benchmark overall. In part 3, we're going to add a human interrupt. So we're going to let us, the user, actually weigh in on the answer and help guide the agent to come to the correct answer. You may consider this cheating, and in fact, we aren't actually going to benchmark this on the whole data set, and the authors don't as well. But in a lot of application designs, what you actually want is the best outcome overall. And so Copilot type setups are a great pragmatic approach to getting a better overall outcome where either perhaps the human alone or the agent alone couldn't actually get there. A big theme throughout this is that autonomous agents really aren't quite there yet, especially when you're just prompting in this simple zero-shot manner. But you can create state machines using frameworks like LangGraph to really control and guide it within your task domain and hopefully get better outcomes overall. Let's download this notebook and then run through it together. All right, now we're ready to start running through the tutorial. We've opened this up in Jupyter, and we're going to install some prerequisites here. It's basically LangGraph. We're going to add some tracing here with LangSmith. The agent is going to be powered by Anthropic's Claude model in our case, and we've got a couple of other things to pull things from the hub. We'll set our environment. In our case, it'll be Anthropic's API key to connect to their API, and then we'll also configure tracing. There's a lot of steps that go on here, and each of the programs can be quite long, so visualizing it in a notebook can be pretty cluttered. I'd recommend using LangSmith just so you can debug each step and see exactly what's happening. It's easier to catch mistakes, easier to see what's going on. We'll then fetch the data we've stored in Google Cloud Bucket, and we'll load it into memory. And then finally, the utility here is to run test cases. I'll note that this is executing code locally, so proceed with caution. There's an inherent risk if the LLM does generate malicious code or something that will have an OOM or something. Example run of the test case runner in this print hello world. If it passes, it'll return passed. If not, it'll return wrong answer along with the expected output. All right, so now I can finally start defining our graph. In part one, again, we'll be doing this simple zero-shot agent with reflection. Note in the paper, they use an explicit reflexion prompt. We've adapted it a bit and then prompted our agent here to be reflecting on its output here when it's doing tool calling. This one's going to be relatively rudimentary. It corresponds to that agent that gets about a 12% pass rate on the benchmark. And so for our first question, we kind of expect it not to pass, but I think that's okay. We've got some other tricks up our sleeve. Now, the next part may be review if you've already built with LangGraph, but I want to review it anyways because I think it is important. The main primitive in LangGraph is a state graph. It's how you define a state machine. Basically, the nodes define the units of work, and the edges define the control flow. Once a node completes, the edge defines which node to pass to next in order to continue operation. In its most simple case, you essentially have two nodes in our cases, and it loops back through, and then will output once it has reached some end state. The final piece of this that's really important is the state, of course. This defines the interface for all the nodes. So each node receives the state as an input and then returns an update to the state. That could be an entire state itself or just some subset that then the graph is able to incorporate into the previous state. In our case, the main aspect of this state is going to be this messages list that we're annotating as being append only using this function, using Python's annotated syntax. This basically keeps the agent scratchpad as it generates a candidate and then receives a tool response and then continues to iterate and try to improve it. The rest of the state here holds the test cases essentially and the runtime limit to configure how the evaluate node runs. The agent itself is going to ignore this, but the test runner will incorporate it. Now that we've defined the state, we'll update our data set to be in the right format essentially to be able to pass it in. And we can start defining the good parts. Remember, this has two nodes. We've got the solve node and the evaluate node. So first, the solver. Here it's pretty simple. We're basically taking a prompt and we're going to compose it with an LLM. So just format into a prompt and then pass it to the LLM. This bind tools operation is just configuring a schema for the LLM so it knows the structure that it should respond with. In our case, we're going to use this write Python tool, this write Python schema. We're basically going to tell it for some reasoning in pseudocode to induce some chain of thought reasoning beforehand. And then we'll finally have it write all of the Python 3 into the code string here. This just makes it a lot easier to parse on the tail end, so you don't have to be parsing out raw strings. I'll run this here, and then we'll define a solver. So we've pulled this solver prompt from the hub. It's pretty simple. I didn't do too much prompt engineering here. Note that we do have this variable examples that we'll use later in part 2. Right now, we're just going to fill this in through partialing with an empty string. That'll be the placeholder that we then populate with additional information that we retrieve, but more on that later. Here's an example run. We're just going to ask it, how do I get a perfectly random sample from an infinite stream? All right, we've gotten the response. So you can see it generates this thinking tag, and then eventually outputs things with the reasoning. You might see the pseudocode, and then eventually the code, and it is doing reservoir sampling as we'd expect. So it at least has studied some code. That's a good initial sign. One thing that I like about Claude as opposed to GPT-4 is that it was trained to output this like thinking or prelude text, you can think of it, before actually doing the tool invocation. I think there's often this question when using GPT-4 with tool calling of how to incorporate chain of thought. And we've found that it sometimes suffers with some of these more complex tasks as a result. I think it's quite nice that they've trained the model to be able to output this before doing the tool invocations, so you don't have to be making sacrifices there. So the second node that we'll define in this loop, this agent loop, is the evaluate node. And there's a good amount of error handling and stuff here, but really the key bit here is we're going to iterate through all the test cases in our state. Again, recall that each node is going to receive an instance of the state and return an output. So in this case, an updated message. But it iterates through the test cases, runs them, and then if it succeeds, it'll update the status in our state. Otherwise, it's going to format each of these things individually and then add the messages. Once you are there, you can create the graph and we'll visualize it. So again, this corresponds to that graph we had above. It's a little more simple. We put the initial problem in here, tries to generate a solution, it tests it out, and then we enter this control edge. If it's successful, we end. Otherwise, we go back to the solver and we keep on looping. Here, the control edge, you can see there, it just also receives the state and then checks that state to see if it succeeded. It then returns, this is a string, end string with double underscores. This just tells the graph that it doesn't need to continue looping. Otherwise, it says go back to the solver node. That's how we would define it here with the conditional edges. Let's see the first question. Question about Farmer John, looking at, it's got some productivity of their day. Bessie got the cow. Seems pretty complicated. It's got some number of sample inputs, sample outputs as a part of the question. Let's try running our agent here. So again, this is the simplest version of the agent that we're going to be building today. I fully expect it not to work, honestly. And the way LangGraph indicates this typically is through a graph recursion area. Basically, by default, the graph has a limited number of steps. You can configure this. We show this in the docs elsewhere. I won't go into detail here. But if it surpasses the maximum number of configured steps, it'll raise a recursion error. Let's wait for this to continue to populate. All right. It looks like, as we said, it's going to hit the recursion limit. Wasn't able to actually solve it. You can see each of these steps below. And we'll actually jump over to LangSmith to check out the trajectory. 1 second. All right. So we've checked out this trajectory here. You can see it going through the loop as we defined it. You have the prompt and LLM, and then you have the evaluate node, and it goes in this loop and continues until it eventually has this error. I always like to jump into one of the later LLM calls because it does collect this full history of messages, and you can see exactly what it's doing. So initially it says, solve this problem, I'll do this, the key insight here, and tries to write out the pseudocode and thinking, and then generates it all there. And then the second one says, oh, the current solution times out in a larger test cases, likely because it iterates through all possible things. So it's trying to actually self-correct here, but is unable to. It doesn't have a lot of good examples of solving this type of problem, I guess, in its memory. And so, as you can see, it goes through quite a number of things. So it wasn't able to get it correct. That's all right. The paper presents at least one more automatic improvement that we can be incorporating into it. And then also presents the idea of more of a Copilot type of scenario, which we'll get to in part 3. But in part 2, let's jump into the memory and retrieval optimization. All right, so back in the notebook, in part 2, we're going to be implementing this few-shot retrieval optimization the paper proposes. And the authors call this an episodic memory because it's retrieving these outputs from the other question-answer pairs in the corpus. So if you pretend that the algorithm or that the agent has already solved all these other problems, it could then recall this and use this for solving later problems. It's kind of an interesting framing and kind of in contrast to the rule of thumb, where people tend to talk about RAG and retrieval as a way to improve knowledge and up-to-date knowledge, but not as a mechanism for actually improving the reasoning capabilities of the agent. Though since these are extremely well-selected, well-crafted, in-domain examples, this does then align more with few-shot instruction and optimizations like that. And this is more of what it is. The paper also explores a semantic memory where it's retrieving over textbooks and things, and that does show a brief boost, but doesn't seem to hold whenever they incorporate that later with the reflection and other things. So it seems to be a technique that doesn't really scale quite to the same extent as this high-quality instruction type of data set. So we'll skip that for here. Following the paper, we'll use as the retriever this BM25 retriever. It's essentially a more old-fashioned, non-vector-based, TF-IDF-based retrieval mechanism here that's high quality. And then to accommodate these steps, we're going to add 2 more keys to our state compared to part 1. We're going to add this candidate message that we generate first, and it's going to be used in the retrieval step. And then we'll have the examples formatted as strings. If you remember the prompt at first, it had that examples template. We'll finally be populating that here. And then again, recall that this episodic memory happens before our agent loop. This part is going to be untouched here. But here we're going to be having the retrieval step. And then we'll still ignore this and save this for part 3. So once we define our new state, we can define the solver. This is mostly repeat from before, except we're going to have a little if statement to populate the candidate step if it's still that first stage there. So we're going to make this draft solver and solver. They're pretty much identical, except the draft solver, of course, hasn't already had questions here. Well, then, to just make sure that we avoid cheating by putting the actual answer to our question in the retriever, we're going to separate out this as train and test corpora, and then we'll create the retriever here. Finally, it's time to define the retrieve node. So as before, it receives the state here, as all the nodes do, and then returns this updated state. So it's going to update the examples key in particular. And then within this, it calls the retriever here. So retriever invoke, picks out the top K there, and then formats this in a string that we're going to be updating in the prompt. You'll notice that we add this runnable config here. In this graph that we're defining, we're going to let you configure whenever you invoke the actual agent, the number of retrieved examples that you'll have. One way to do that is through these configurable params in the config, which is always the second positional argument. One more thing to note about this retriever setup that I think is quite interesting is that we're treating the candidate program as the query rather than the initial question. This is kind of similar to techniques you might have come across, such as hide or some of these other like raft or other types of indexing strategies for RAG. The observation here is that the distribution of queries is different than the distribution of documents that you're trying to retrieve from. And so you either want to be creating hypothetical queries from the documents that will better align with types of queries that we're going to be putting into the system, or we want to map from the queries to what you'd expect the document to look like and then maybe retrieve from that. And then there's some other variant there. But basically you're saying the type of text and the type of words that we're going to put in these two things is not going to be the same, and so you get better results if you can try to translate them. Finally, it's time to build a graph. So again, we've had most of this is the same here. So you see solve, evaluate, and like all these stuff is like untouched. The things that we've added here really are this draft node at the beginning where we're putting in that solver, and then the retrieve node here. So we're setting the draft node as the entry point, retrieving, and then we're going to always progress in a directed edge from draft to retrieve, and then retrieve to solve. And then again, we'll create the loop of solve to evaluate, and then from evaluate, either go to the end or back to solve. So we're creating that. Here's the visualization in case that's easier to see. So again, the rest of this is all the same. We've just added these 2 steps at the beginning. Let's try it out. We're going to, since we added a checkpointer here, we're going to add, just you can ignore this here, but we're going to say retrieve 3 of these examples from the corpus and pass those in. This is also going to take some time, so bear with us. All right, looks like our graph finished already. You can see this is a little bit truncated. Let's jump over to LangSmith to see what exactly was done. But you can see that from the state that we've got, you can see that it was a success this time. All right, now we've jumped over to the LangSmith trace. You can see it's only a few steps this time, so that's great. And following our graph structure, we had the draft node here, which again, you put in the initial question, the system prompt, the question, and it outputs the initial answer to the problem. We retrieve some examples from it. So again, see the query is this candidate program that we talked about, and it retrieves other examples from the corpus. And then we pass that in here. So you can see now those examples are formatted here in the system prompt for the solver. And then it has that. All of it, we don't have the initial candidate program in here because we've saved it in a different key in the state. But then it tries to generate an answer. This time it's correct, and test cases are successful. So that's great. I'll jump back to part 3. Because we see it solves this bronze level question, but how well does it solve some of the more difficult, challenging ones in this benchmark? All right, so jumping back to the notebook, let's test it on a harder silver level question. So we've got this from the dataset. You can see the question here. So River Cruise 1, basically you're trying to detect cycles and then simulate different steps of it as well. It gives a couple of sample inputs here, but it's a much more challenging question than the first one here. We'll format that and then run it, and we'll see how it does. I fully expect this not to work. It may, but I expect this to fail because it's just a more challenging problem. And these LLMs, while they have been trained on a lot of code, a lot of reasoning types of problems, whenever there's new ones, they just kind of struggle to be composing them in creative ways. So some of these techniques can help, but I think we're running into some of the limits of the reasoning capabilities of agents as they stand today. All right, so our optimized graph has finished, and we got another graph recursion error. It wasn't able to correctly answer the problem in the allocated number of steps. That's okay. In fact, we expected it. These are extremely challenging problems, and they push the LLMs, at least as they're trained and designed today, to the limits of their reasoning capabilities. It requires some novel combination of algorithms and data structures in challenging ways. The paper explores then one final inference time optimization, which really gets us from the realm of autonomous agents to the realm of copilots. So that they can benchmark it, they restricted human involvement to simple guidance and prodding without revealing any parts of the answer or anything. But when you're building an actual application, you often want to optimize really for the end user experience and maximizing the chance of accomplishing the goal. If you are going to be creating an application where a user is in the loop, you want to give them a nice ability really to be providing guidance whenever and wherever they want. LangGraph makes this pretty easy. So for the sake of this tutorial and in part through, we're just going to add a generic human in the loop interface to our agent, and we're going to insert it right here. So the agent graph is going to be structured exactly the same way as part 2. We'll insert the problem, the agent will generate a candidate program, the program will retrieve similar high-quality examples from this corpora of semantic memory or episodic memory, and then the agent tries to solve it. It generates the program here. It then runs the test cases on them. Then what we're changing in part 3 is we're going to interrupt here, and then we'll say a human is allowed to then look at the state of the graph at this point, perhaps optionally add a message saying to consider some alternate route, consider looking into a specific part of the generated program, etc. We can then resume execution at any time, since LangGraph lets you just persist this in a checkpoint, and continue trying. You can continue this loop and continue to intercede and provide feedback as it goes through, and hopefully prevent the LLM from falling into these local optima, these local pit holes where it's just looping through and unable to actually accomplish the real task. Once you can collaboratively come to the final answer, the agent and the graph can finally finish executing. In theory, this type of design is only restricted by the quality or the capability of the user involved, since really we can be providing the correct answer or any type of feedback, and the LLM will be able to synthesize this and incorporate it into it. So let's jump into here and create this human-in-the-loop agent for solving computing Olympiad problems. This code block here is exactly the same as in part 2. We get our checkpointer here. We're just going to do that in memory. We've got our state graph. We're using the exact same state here. We've got the prompt in LLM. We create this draft solver, add it to the node. We set that as the entry point. We create the retrieve node. We create the solver node and the evaluation node to run the test cases. Then we start connecting them. So we add an edge from draft to retrieve, retrieve to solve, solve to evaluate. And then we add these conditional edges to define the conditional looping. So we say, once you run the test cases, we'll either go back to the solver or we'll finish if we succeed. And we'll create the checkpointer as well. The one different thing in part 3 compared to part 2 is we're going to add this interrupt after the evaluation node command. So basically, before it goes to a human step, we're going to tell the graph, hey, stop and allow the human or any other process to be modifying the state. Let's visualize this here. As you can see, the graph looks exactly the same as in part 2, and we'll start running it. So again, this is just going to continue executing until it reaches that interrupt. All right, so our graph has stopped executing. You can see the current state by looking at this snapshot using the config. You can see again the problem there. Note that it doesn't say a graph recursion error, but it still has gotten the incorrect submission as we expected. Since we added the interrupt, it actually will stop this loop, and then we can resume it at any time. So we can look at, again, here's the silver problem that we were looking at before. It was unable to solve it so far. We're going to look at its current candidate solution. So this is again printed out from the agent right now. Looks okay, maybe a little simple. Definitely doesn't handle all of the edge cases. And then we can look at this test here, because that's the last tool message here. Incorrect submission. I actually got 8 out of 10, so pretty close. Let's give it some recommendations here as a human message. And then we'll check to make sure that that actually was reflected in the state. So you can see we now have this human message we've done by calling graph.updateState and providing that config there. So it tells which snapshot to be updating. And then you have the human message here, and we can resume. The way we resume here is we pass in a null value, so none. And then since we're using this same config that we're using, it knows to load the current state from the check pointer that we've compiled into the graph. Again, we used that in-memory SQLite check pointer here for the sake of the tutorial, but there's a lot of implementations you can use to connect with your own storage architecture. This is going to take a little bit of time, so again, we'll resume whenever it's done executing. All right, so in our case, it actually was enough to get it to succeed. I had this other code here to try to prompt it into the right position, because occasionally it doesn't succeed even after that first bit of human feedback. But in our case, it does. As you can see, you can list through all of the states here. So I was just getting the most recent checkpoint from this graph's execution, and we see that it's a success. You can actually check out the Langsmith trace again here. I'll jump back to see it run. And we see that, again, we passed in null, if you remember from the loop in the notebook. It goes, it loads, we go back to the solver, because that's the next node slated to be executed in our graph. It already run the draft and recall and retriever and all those steps. You can see the full list of messages to see that, yes, indeed, it has been fetching these things from memory, and includes this recommendation that we've added. We've put this all in a notebook, but again, you can put in any sort of UI above the LangGraph implementation and allow the user to be interacting with your Copilot in arbitrary ways. So the AI is able to then incorporate this breakdown into an updated response that then passes all of the test cases. So I'd say it's a success. All right, so that brings us to the end of this tutorial. As we saw, LLMs as they're trained today alone aren't super great at solving this challenging type of reasoning problems posed by Olympiad programming questions. However, through some prompting techniques and then better systems design, you can improve the average performance greatly from the low point of under 9% to above 20%. And when you're building real applications to solve challenging problems, you can create these sort of human-in-the-loop interfaces easily with LangGraph to make it so that you can reach a better overall outcome compared to just the agent alone and compared to just the human alone. I think these general techniques are fairly expansive and can be applied in a lot of domains. So you recall, first we started with a zero-shot agent with reflection. It basically prompted the agent to be looking at the test case results, looking at the current solution, and then try to incorporate those results and feedback into an updated candidate to eventually get out and solve the right problem. We saw how even on a bronze level problem, this doesn't always work. And so we then added in an additional optimization for retrieval. This, as the authors posed as like sort of episodic memory, allowed the model to then fetch these really high quality examples from the corpus and use that to try to trigger a little bit better of an output that follows a similar design and approach. This can induce better reasoning in this case because of these few-shot instructions. We saw that that was able to solve the bronze level question, but it failed on the silver level question. So then we added in this human-in-the-loop interface with the interrupt after that allowed us to then go in and modify the checkpointed state of the graph to then guide the agent to come to a proper solution to the problem that is hard. As you can see from all of these steps, autonomous agents are really cool. They're not quite there yet on a lot of these challenging problems. But through better engineering, through using state machines and all of this, you can come to some better designed systems that are actually capable of doing some pretty impressive work. I'm excited by this new data set because it is just a lot more challenging and shows the cracks in the abilities of our current types of language models as they are today, while also showing how these hybrid systems, these neurosymbolic approaches, can be really powerful in improving performance. I'm excited to see other people come out with better systems that can surpass those presented by the authors and hopefully get to the point where they can solve all these types of questions, even without resorting on like much larger models. That's all that we have for our tutorial today. If you have any questions or comments, feel free to leave them in the comments below. Check out the links in the description as well to see the code and run it for yourself. And let us know what other types of tutorials you'd like to see that would be helpful in implementing your own agents and chatbots and assistants. Until next time, this is Will, and hope you have a great day. Bye.